I'd like now to build on what we've been learning about field lines, but to take on the topic of conductors, to introduce that for the first time. And I'm going to introduce conductors through actually an example. So this is our new topic, conductors. And here then is the example that I want to consider. I'm going to leverage our previous field line example, actually. I'm going to use a cylindrical setup like we've seen before. I'm just going to draw the edge-on view, though. It starts to become a little difficult to understand the perspective of the diagram when I keep drawing what's going on in back. So this is just going to be the edge-on view. But I think we've played with this cylindrical case before. You should have a pretty good intuition, at least, of what I'm drawing actually here represents. So what I'm going to have then in my edge-on view is the line of charge is just going to appear as a dot, and I'm going to continue to have that maintaining a charge plus 2 lambda. Now what's going to be different is the cylindrical shell that I put around this is now going to have some thickness like a metallic pipe, and it's also going to be conducting. So a metal pipe is not a bad representation. So that's going to then have to be represented by a circle. So that's the inner part of the pipe, and then out here I have the outer edges of this pipe. And this pipe then actually I should fill in a little bit, right, to indicate that this is actually solid chunk of conducting material. And that pipe itself, onto it, I'm going to put a charge of minus lambda. Now, the interesting thing about conductors, as you know, is that charges are free to move however they like when they are in a conductor. So we have to try to figure out now how exactly it is these charges minus lambda are going to distribute themselves within this conductor for this situation, while at the same time we're trying to sketch the electric field line. So it's sort of like two things that all have to happen all at the same time. Now, our first guess, and it's not an unreasonable guess, would be that, well, I've got this charge minus lambda on my conductor. It's a negative charge, and I've got a charge of plus 2 lambda in the center of the conductor. So my first guess might be that all these negative charges are going to be attracted to that inner surface. So let me sketch that here as our guess. So this is our first guess. And that would be then where I've got plus 2 lambda in the center. I have the shell that I'm trying to draw here, right? Looks something like this. That's the inner surface. Here's my outer surface. Apologies for the diagram not being perfect. And I'm thinking, okay, I'm likely going to have charge minus lambda distributed on that inner surface of my conductor, something like so. And now this is a situation for which we have sketched the field lines before. Here, I'll try to put those there for you in red. And then these field lines, we knew what happened was that I had 8 of them. That's just how I chose to represent 2 lambda. That would be coming out from the central positive wire, because fluid or electric field lines always originate on positive charges. And then if I have minus lambda distributed around the edge, that's enough just to suck up 4 field lines, half of those field lines. So maybe again I'll choose these diagonal ones to be, in my sketch at least, the ones that I use to represent the field lines which end. And then I would have these field lines continuing off to infinity. So that would be my initial guess for this situation. But now there's something very interesting happening here, because I am dealing with a metal, with a conductor. And the interesting thing has to do with what's going to happen in the conductor in the vicinity of this field line. This field line, remember, is always tangent or parallel to the electric field. That means that I am, in my guess, asserting that there is an electric field inside this conducting region, pointing off to the right. Now, if there were such an electric field, what's going to happen is that if there were any positive charges that were free to move in this conductor, because conductors have a supply of charges that they can shift around within themselves. Any positive charges would tend to move here off to the right, and any negative charges would tend to move off to the left. And whichever kind that the conductor has. Notice if it's negative charges that are moving off to the left, that would leave left over some positive charges that my negative charges are abandoning, that would leave positive charges on the surface, which is equivalent, in fact, to positive charges flowing outwards to the surface. So it doesn't matter. You can analyze this either way you want. You will come to the same conclusion that ultimately what's going to happen is, and let's just take this as a metallic case, and in normal metals it is actually the negative electrons, which are the charge carriers. I'm going to be concentrating the negative charges on this inner surface. And those negative charges, new, additional negative charges, I've already accounted for these ones here in the corners. Right? So as these negative charges come and concentrate on the surface, they're going to start to eat up and block this field line. And that process is going to continue until I build up more negative charges on the surface than I had been initially expecting, but I have to generate just enough negative charges there so that I can stop that field line. Because as long as that field line exists within my conductor, negative charges are going to travel, right? They travel in the opposite direction from the electric field. So those negative charges are going to travel downwards along that field line until finally that field line has to be eliminated. So let me try to erase my field line there, like that, right? So the field line then has to stop. And that process would happen then at each of my different field lines. Negative electrons are going to travel through the conductor and gather on that inner surface until they are able to block the field line. So there'll be an extra concentration of negative charges there, which means, though, that they must have abandoned or left some positive charges on the outer surface, which is a good thing, actually, in terms of my diagram, because if there are positive charges there, which have to correspond in number to these new negative charges that are concentrating on the inner surface, that then provides an anchor point where a new field line is going to have to originate. And I can continue this way, going around my conductor, right, bringing in those negative charges to stop those field lines, leaving some positive charges. And I will do that here as well, negative, and then there'll be some positive charges left over on the outer surface of the conductor. Now, you'll notice I've kind of anticipated that the positive charges all end up concentrated on the surfaces of the conductor. There are not going to be any, at least that's what I'm asserting, positive charges left over inside the conductor. And the reason for that is that if there were a positive charge left in the conductor like that, we know from our field line rules that such a positive charge would actually generate field lines. But those field lines, again, would represent outward pointing electric fields, which would immediately attract negative charges that would then move down those field lines until they finally canceled out any positive charge that would be left in the center, and that whole unit would then disappear. So what I'm expecting then is that these extra minus charges, their positive partners, have to be distributed in equal numbers, namely 4, all around the outside of my conducting surface. Because I have positive charges there, those do represent sources, right? So there have to be field lines coming from them. You can't just have a charge sitting somewhere without an attached field line. Those field lines can't be pointing inward into the conductor. We know that because, again, you can't have a field line in a conductor. The moment there's a field line in there, negative charges are going to climb up that field line in order to cancel it out. So the only way the field lines can go that come from these positive charges on the outside of my conductor would then be outwards towards infinity. So that then would complete my sketch and gives the rationale for how I would draw the field lines for a conducting case such as the one we've been considering. Now, I know that was a lot of information all at once. There's certain lessons that we can draw from this. And I want to spend a little time just emphasizing those lessons to make sure we're getting the main points across here from the reasoning that I just gave. So the first lesson, number one, is that the charges, because they are free to move in the conductor, charges are going to adjust until there are no field lines in any conducting region, in a conductor. Another mathematical way of saying that is that the electric field actually has to be zero in the conducting regions. That's the first thing that we saw. That was this fact that all the free charges were able to climb up these field lines and terminate them then on those surfaces. The second rationale that we gave in coming to our final conclusion is that there can be no uncompensated charges, and I'll define what I meant by uncompensated in a moment, charges in conducting regions. Mathematically, I'm saying that the charge per unit volume anywhere inside a conductor equals 0 in a conductor. Now, by uncompensated, what I mean is that, of course, in any material, if I look very, very microscopically, there are going to be electrons and nuclei, right? But the material overall, generally speaking, is going to be neutral because every atom will have as many electrons as there are protons in its nucleus, so it remains a net neutral object. By uncompensated charges, I mean situations where, as I was considering here, maybe there might have been a positive charge. That would have meant there was an atom that had lost its electron and become an ion. And what we're saying here is that that is not possible, because if there were an uncompensated charge, that would generate an electric field inside the conductor, which would immediately generate motion in the conductor, attracting negative free charges, which would then immediately cancel that effect out. Now, the consequence of this, though, of number 2, is that if I put charge on a conductor, which is how I started off my problem, or if I put something like in a hole inside a conductor that requires the conductor to generate charges on its surface in order to prevent the electric field from penetrating into the conducting region, I can build up charges on a conductor. What number 2 just said is they can't be in the conducting regions, right? They can be, though, on the surfaces. So lesson number 3 is that all uncompensated charges on a conductor must be on the surfaces. So we can have a surface charge density on a conductor, but we can have never any net volume charge density. So there can certainly be surface densities. And to give the mathematical statement, surface densities are possible. You can have sigma on the surface. Charge per unit area can be not 0 if the situation demands. Very good. So this then wraps up our lessons for what happens when we combine field lines with the physical behavior of conductors.